Hello everyone, my name is Jinnan Zhang from Institute of High Energy Physics and the University of Chinese Academy of Sciences. Today I'm going to give a talk on the JUNO oscillation physics, representing the JUNO collaboration. This talk consists of the following parts. Firstly, I will briefly introduce the multipurpose experiment, JUNO, and the physics of neutrino mixing and oscillation. Then I will show you how JUNO explored the neutrino oscillation physics with the reactor, atmospheric, and solar neutrinos. And finally, I'd like to give a summary. The Jiangmen Underground Neutrino Observatory, known as JUNO, is a multipurpose underground liquid scintillator experiment located in Guangdong province, South China. The primary physics goal of JUNO is to determine the neutrino mass ordering with the reactor neutrinos. Thus, the location is optimized for the neutrino mass ordering determination. It is about 52 kilometers away from the Yangjiang and Taishan nuclear power plant, with totally 26.6 gigawatts of thermal power. And at the same time, JUNO can also detect atmospheric neutrino, solar supernova, diffused supernova background, and geoneutrinos. This talk will focus on the oscillation physics with the reactor, atmospheric, and solar neutrinos at JUNO. With such rich physics expectations, the detector is designed and built as follows. The 20 kton liquid LAB-based liquid scintillator are filled in the acrylic sphere, around which we will install plenty of 20-inch PMTs and 3-inch PMTs to achieve about 80% optical coverage of the detector. And the massive volume and the high optical coverage will provide us large statistics and exceptional angular resolution, which are two of the most important factors in the physics measurement. Besides that, we have designed a comprehensive calibration strategy to control the end scale uncertainty to be within 1%. And to control the background, we made a very detailed and strict requirements on the reactivity of the materials and components of the detector. And now we're familiar with the JUNO detector. Let's move to the physics side. Neutrino physics is one of the most successful disciplines in the particle physics, allowing us to probe the physics beyond the standard model of elementary particle physics. And thanks to the past several decades experiments, we know that neutrinos are massive and may oscillate during the propagation, which can be described by the so-called PMNS mixing matrix. And we have measured some of the mixing parameters, and there remain several open questions. One of the most urgent and important is that the neutrino mass ordering. That is, whether the mass eigenstate nu3 is heavier or lighter than other two. And this question is the primary physics goal of JUNO. Next, I will show why JUNO can answer this question. The reactor neutrinos at JUNO are mainly electron anti-neutrinos generated by the reactors. The fission interactions of mainly 4 isotopes in the nuclear power plant are the source of them. And here is a list of thermal power and baselines for the reactors that contributes about 99% of the reactor neutrinos for JUNO. The neutrinos travel through the Earth to the detector, and during which we can apply the neutrino oscillation theory to calculate the survival probability for this kind of electron anti-neutrinos. And in the right figure, you can clearly say the oscillation effect on the neutrino energy spectrum, and how important the energy resolution for determining the neutrino mass ordering. And at JUNO, the neutrinos are detected via inverse beta decay interaction. After this interaction, the positron will bring most of the neutrino energy and give a prompt signal to the detector. The neutron will be captured by hydrogen after about 200 microseconds and will give a delayed signal. The correlation between the prompt and delayed signal helps us to select the signal and suppress the background. And since the positron will bring most of the neutrino energy, we choose the observed positron energy spectrum by the detector to extract the neutrino oscillation physics. And for given neutrino energy, The positron distribution is relatively flat and has a ways. And due to the excellent angular resolution of JUNO detector, we will have to take this nuclear recoil effect into account as shown in the left figure. And the positrons will deposit energy in the detector and generate the photons by scintillation and Cherenkov radiation processes. And the photons are collected then by the photomultiplier tubes and will be converted into photon electrons and read out by electronics. The observed visible energy is proportional to the total number of photon electrons and is not linear with respect to the total deposit energy of the positron. The nonlinearity relationship is noted as liquid scintillator nonlinearity here. And the angular resolution effect of JUNO is described with the classical electromagnetic calorimeter formula and can be well calibrated. This figure on the right shows the angular spectrum on different detector response effects. Based on the characteristics of the IBD interaction, we designed a series of selection criteria to select the reactor anti-neutrino signals. And the combined space, energy, time selection will tremendously suppress background rate. Here is estimation of the spectral and rate of the background for the reactor neutrino analysis. Apart from the main detector, JUNO, we have a satellite detector near the Taishan power plant, which is the Taishan anti-neutrino observatory. Is about 30 meters away from the Taishan reactor core, and we operate at -50 degrees with about 2% angular resolution. The initial purpose of this TAO detector is to provide a reference for the JUNO and to control the shape uncertainty of the reactor neutrinos energy spectrum. And the right bottom figure shows the power of the TAO detector. TAO detector is also able to test the stereo neutrino hypothesis. With all the reactor neutrino components above, I will next show you the physics sensitivity of JUNO. The first that comes to us is the neutrino mass order determination. By considering the most recent knowledge of this detector, we found that the meteor sensitivity for JUNO on measuring the neutrino mass ordering is slightly larger than 3 sigma for 6 years of data taking. Apart from using the reactor neutrinos data of JUNO, it is also shown that JUNO has the potential to reach 4 sigma in 6 years by adding the external constraint on the mass splitting 3.2 or 3.1, or equivalently, JUNO can reach 3 sigma in less than 6 years. And we are currently preparing the paper on this, and that will come to the public soon. Together with the measurement of JUNO, the combination of JUNO and other neutrino experiments has a great potential on determining the neutrino mass ordering. With the optimized baseline, JUNO can say both fast and slow components of the neutrino oscillation. Therefore, JUNO can measure 3 of the oscillation parameters to an unprecedented level. In the right figure, you can say that JUNO will dominate the precision of the mass splitting 3.2 or 3.1 sine squared theta 1.2 and mass splitting 2.1 in 1 year, and measure them to the sub-percent level in 1 to 2 years. And with 6 years data taking, which is nominal periods for JUNO to report the neutrino mass ordering sensitivity, the precision of JUNO on the oscillation parameters will be better than 0.5%. It will be even 0.2% for mass splitting 3.2 as 1. This measurement will provide an essential information for neutrino oscillation physics, and we are also preparing a paper on this that will come to the public soon. As a multi-purpose detector, JUNO will also see several atmospheric neutrinos per day with the flavor identification, direction, reconstruction ability, and the resolution of JUNO. We have the phase that JUNO will provide a complementary measurement of the neutrino mass ordering, the octant of the mixed angle 2-3, and the CP violation phase when started data taking. And now we're working on the even construction of these atmospheric neutrinos. JUNO can also catch the neutrinos from the sun via elastic scattering. To reduce the background and send such signal in the detector, we will purify the liquid scintillator to control the radioactivity in the detector. And for 10 years then taking, JUNO will detect about 60,000 neutrino signals and with approximately 30,000 background events. The data provides us opportunity to measure the day-night asymmetry with about 0.9% sensitivity, which is better than the current Super K experiment. And they can also independently measure that mass splitting to 1 to about 20% precision, and the mixing angle 1,2 to about 8% precision. And now let's sum up what I went through in this talk. As a multi-purpose experiment, the oscillation physics of JUNO can be divided mainly into two categories: the neutrino mass ordering and the precision measurements of the oscillation parameters. And for the mass ordering determination, JUNO can reach 3 sigma significance in 6 years with only reactor neutrinos. And so the sensitivity of the atmospheric neutrinos is larger than 1 sigma for 6 years data. And for the oscillation parameters, the precision will be measured to the sub-person level with the reactor neutrinos. And the atmospheric neutrinos will also provide a measurement on the mixed angle theta to 3, and the solar neutrinos can provide an independent measurements on the mixing angle 1, 2, and the mass splitting to 3. The satellite detector TAO will provide a high precision measurement on the reactor neutrino and spectrum and explore the stereo neutrino hypothesis. Finally, JUNO will start data taking in 2023. Thank you very much for your attention.